A very patient woman wishes to become a billionaire. She decides to follow a simple scheme. She puts aside 1 cent the first day, 2 cents the second day, 4 cents the third day, and so on, doubling the number of cents each day. How much money will she have at the end of 30 days? How many days will it take this woman to realize her wish? So let's go ahead and start off with just looking at the 30 days. So 1 cent, that was weird, 0.01 plus 2 cents, 0.02 plus 4 cents, 0.04, and so on. And we're doing this for 30 days. So this we see here, the pattern, of course, is we're doubling, as it says, which means that this is a geometric sequence. Now, for a geometric sequence, the sum of the first n terms is the first term times 1 minus the common ratio r to the n, all over 1 minus r. So we know our first term is the 1 cent, 0.01. 1 minus the common ratio is 2, and n is 30. We're doing this for 30 days, all over 1 minus 2. And this will tell us the sum after we've added all of that up. So we plug this into our calculator and we get, let's see, 1073741. Oh, that's not 737 418 and 23 cents. Okay. So that is $10 million. $10 million, $737,418 and 23 cents. Not too shabby, the end of 30 days. Then we'd like to know how many days it will take this woman to realize her wish of becoming a billionaire. So we want to take our sum, and we don't know n anymore. We don't know how many days this will happen. But we know that we want to end up with a billion. So we're going to take our sum and set it equal to a billion. So 1,000 million billion equal to that first term, 0.01, times 1 minus 2 to the n, we don't know that n, over the 1 minus 2. Well, we can do a little bit of simplifying here first. First of all, this is just a -1 in the denominator, and I can just apply that to the numerator. So I have my 1 billion equals a negative up here, which I'll distribute into the parentheses there, 0.01, and then 2 to the n minus 1. Okay, now if I divide by 0.01, that's dividing by a 100th, or multiplying by 100. So it's going to add on a couple zeros here. So it's no longer going to be a comma there. 100. Okay, so now we're looking at 100 billion equaling 2 to the n minus 1. And we can, of course, add 1 to both sides. So 100 billion and 1. We're looking for 2 to the n to equal that. All right, well, you could just plug in different powers of n here to see how many times you can multiply 2 by itself to get 100 billion and 1, or we can use logarithms. Let's go ahead and use a logarithm. I'm going to do, so we've just log of 100 billion and 1, and that's equal to log of 2 to the n. And remember, the logarithm allows us to pull the exponent out in front. So this is actually now an n in front of the log 2. So n log 2. And then to get n, we can divide by log of 2. So divide that by log of 2, and that'll be n. So let's go ahead and plug this into our calculator. And so I've got log of 1 billion. Let me make sure I'm getting correct in my numbers here. So got 100 million, billion, and 1. Great. And then we divide that by a log of 2. Okay. And we get about 36.54. So remember that we're talking about number of days here. And so this is 36.5 days, but of course she's only doing like this once each time per day. So we would need to round up then, and it would take a total of 37 days to reach our $1 billion with this pattern.